Alright, we have this second order homogeneous differential equation, which is the Helmholtz equation in 1D, and we want to find what is the general solution. Here I'm just going to give you a hint. The characteristic polynomial for this one is lambda squared plus k squared, or you can write it lambda squared plus 0 times lambda plus k squared. The discriminant here is what? 0 squared minus 4 times 1 so it's 0 squared okay. It's 0 squared minus 4 times 1 times k squared. That's minus 4k squared. Which is a negative quantity. And if we have a discriminant which is negative, then the general solution, you find lambda 1 equals and lambda 2 equals so it's minus 0 plus square root of minus 4k squared over 2 minus 0 minus square root of minus 4k squared over 2. These are going to give you some complex numbers. I'm not going to write them down. And the general solution is going to be C1 E real part lambda 1 times t cos imaginary part lambda 1 times t plus C2 E to the real part lambda 2 times t times sine imaginary part lambda 2 times t. This is going to be the general solution. C1 and C2 are going to be real numbers. Our real lambda 1 is going to be the real part of the lambda 1, which is a complex number, and im of lambda 1 is going to be the imaginary part of lambda 1. Real part of lambda 2 is the real part of lambda 2, which is a complex number, and imaginary part of lambda 2 is the imaginary part of lambda 2. One more hint: lambda 1 and lambda 2 are conjugate complex numbers. Which means that the real part of lambda 1 equals the real part of lambda 2, and the imaginary part of lambda 1 is minus the imaginary part of lambda 2. That's the hint, and you fill the rest of the details there. So you have to find what is lambda 1, lambda 2, find the real parts of lambda 1 and the imaginary part of lambda 1, real part of lambda 2, imaginary part of lambda 2, plug them in and find what is the general solution, which is going to be of this form here.